right. Hello, class. It is Friday night, and next week we are going back to in-person school, and I am pre-recording a lesson for the day that you are not in class. Um, so I'm going to go ahead and get started. Excuse me. So this is for my CHL classes. So what we're going to be talking about this evening is capacitors. Okay, and so before I explain what a capacitor is, I'm going to remind you about the infinite plane of charge. Infinite plane of charge. So if we were looking at an infinite plane of charge from the side, we would see it edge on, and if it's a positive infinite plane of charge, we used Gauss's law to calculate that the electric field is sigma over 2 epsilon naught, where sigma is the charge per area of the infinite plane. Okay, so that's charge per area. And so the electric field points away from the plane like that because it's positive. Ooh, maybe there's some people watching. Say hello if you're watching. You also have nothing to do on Friday night. So there's that. Now, what if we were to then put a infinite conducting plane below that that has the same charge density but opposite? So it's minus. All right. The electric field is going to have the exact same magnitude, but it's going to point in the opposite direction. Instead of pointing away from the conducting plane. Oh, hey, Fu. Instead of pointing away from the infinite conducting plane, it's going to point towards the infinite conducting plane. So it creates its own electric field that points in towards itself, like that. All right. So here's what happens. Now, both of these electric fields extend throughout all space, okay? So if we look at up above these two planes, the negative conducting plate is creating an electric field that is downward, and the positive plate is creating an electric field that points upward. So up above the two plates, these two electric fields cancel out and they make 0. Okay? Down below the two plates, the negative one makes an electric field that points upward, but the positive one makes an electric field that points downward. And so we can see down below the two, the electric fields also cancel each other out. And this depends on the fact that these are equal charge densities, equal in magnitude but opposite in size. So now, if we look in between the two plates, these two electric fields are they're both going downward, so they're going to combine, and we'll get a total electric field of size sigma over epsilon naught. Okay? So that is what a capacitor is. All right? It is two conducting planes with equal and opposite charges between them. Or on each plate. They're usually called plates in the context of capacitors. Okay, so if we look at an actual capacitor, it's got two plates. All right, one of them has a charge of plus Q, the other one has a charge of minus Q. The electric field goes from the positive plate to the negative plate, and it is constant in between the two capacitor plates. So the value of that electric field is sigma over epsilon naught. So now this is two infinite conducting planes, but a capacitor, these are finite conducting planes. Okay, so so actually, what happens is at the edge of the capacitor, the electric field kind of bows out like this. All right, and so this is called the edge effect, but so-called edge effect. However, in most situations, the edge effect is not significant, and so we're going to ignore the edge effect. All right, but you should know that it's there. So so this is a capacitor. It's two conducting plates with equal and opposite charges on them. There's an electric field between them. Now, if we wanted to calculate, so let's calculate the potential difference between the plates. I'm going to box this in so you know that that's the case. What is the potential difference between the plates? Well, we know that electric field, okay, is electric field is equal to the change in electric potential divided by the change in distance. Okay, and I'm going to deal with magnitudes, so I'm going to drop the minus sign. Okay, so the magnitude of the electric field is now the electric field between the plates is approximately constant because the spacing of the electric. The only thing that makes it not constant is the fact that these plates are finite. But we know that if it's infinite conducting planes, then the electric fields are constant everywhere. But for the most part, it's approximately constant between the plates. So this is going to be the potential difference between the plates divided by the distance between the plates. And that's equal to the magnitude of the electric field, which is sigma charge per area, okay, divided by epsilon naught. So I can rearrange this equation, and I get Q equals epsilon naught A over D times the potential difference between the capacitor plates. Okay, so that comes from rearranging, doing some multiplying. Now, this thing right here, notice how it depends on the area of the capacitor plates, and it depends on the distance between the capacitor plates. So this depends on geometry, all right? It depends only on how we construct these capacitor plates. Are they circular? Are they square? Are they close together? Are they far apart? That's the only thing that depends on. So this factor is called the capacitance, C. And so normally we write the equation for, this is the fundamental equation for a capacitor, is Q equals CV. All right? Where Q is the charge, this is the charge on one of the plates, okay, on the positive plate. The total charge on both capacitor plates is 0 because they're equal and opposite. Charge on one of the plates, okay. V is the voltage between the plates. All right. And C is called the capacitance. And C is equal to, just by comparison between this line and this line, it's equal to epsilon naught A over D. Okay, so that's equal to C. The units of capacitance, you can see based on this equation that it's coulombs per volt. And that has a special name. It is called the farad, which is abbreviated by F. All right, so this is the capacitance. Now, because these capacitor plates are oppositely charged, they are attracting each other. So if these were just free-floating capacitor plates, they would just go like that and attract. So we kind of have to either hold them apart, or we have to put something that's not conducting between the plates. And so that's what's usually done, is we put something between the capacitor plates that is not conducting, that's an insulator, that keeps the capacitor plates apart. So if we were to actually look at a capacitor, it has something in between the two plates, like this. So something is in between the two plates, so that they don't go like that. And that insulating thing that is between the two plates is called a dielectric. Okay, a dielectric. And because of that, the dielectric has the effect of increasing the capacitance above this value. And the reason is that now that we've put the dielectric between, we don't have free space. So remember, epsilon naught is the permittivity of free space. So if we put something else that's not a vacuum between the two plates, we no longer have free space. And so there's a relative, just like when we were talking about solenoids with the relative permeability when we put iron in the middle of the solenoid, there's also a relative permittivity when we put something between the capacitor plates. And so this equation, we also have a relative permittivity, okay? And so it has the effect of raising the capacitance. All right. Now, so the question is, well, how do we get charge on the capacitor plates? All right. Usually, well, so what happens is we've got wires that go out of the capacitor plate, okay? And then maybe those wires are connected to a battery, okay? And so the battery, as we know, pushes positive charge out of the positive side of the battery. And so what will happen is the battery will take positive charge off of the bottom plate and push it onto the top of the plate. Okay, so the top of the plate, the top plate has a buildup of positive charge, and therefore there's negative charge on the other plate. Okay, and then what we could do is we can then remove the battery. Okay, so we remove the battery, and when we do that, so here's the capacitor. So we've removed the battery, so there's still these wires there, but there's no battery anymore. And the charge is just going to stay there. Okay? Why? Because this isn't the space between the capacitors is insulating, so the charge can't jump between the capacitor plates, and it can't go around the other way because that pathway is no longer there. Okay? So the charges are just kind of stuck. All right? And then later on, if you were to then, so these charges will just stay on the capacitor plate indefinitely. All right? This is actually something, if you are like messing around with old electronics, there could be capacitors in those electronics that are still charged. And so it can actually be dangerous in some cases, right, to just go probing around in old electronics. Because what happens if you then connect the terminals of the capacitor with no battery? Well, then what happens is the charge says, all right, I can now, the charge can now, it can't go directly from one side to the other, but now it can go around. And so the charge, remember in circuits, it's the electrons that actually do the moving around. So the electrons will go around like this, and the electrons will go around and they will cancel out the positive charge on the top plate, and then you will have what's called discharging the capacitor. All right, and so when you discharge the capacitor, you can see that when you connect the two terminals of the capacitor, the charge is going to all of a sudden move. And so when you discharge the capacitor, you get a burst of current. All right? You get a burst of current. And that's from discharging the capacitor. So I think that's kind of interesting. So basically what capacitors do is they, and I'll write this here, capacitors store electrical energy. Okay, they store electrical energy, and then so basically a capacitor is going to store electrical energy. Now a battery is somewhat different because a battery gives you electrical energy, but it's actually storing that energy in the form of chemical potential energy. So you're taking chemical potential energy and turning it into electrical energy. With a capacitor, on the other hand, you are storing it as electrical potential energy. Okay? So it's already in, it doesn't need to be converted into another form of energy. Okay, so capacitors store electrical energy. And then they can give it back to you in a burst of current. So the natural next question is, well, how much energy? Okay, so let's calculate it. And we're going to be using this equation. So you might remember that the definition of electrical potential energy is charge times voltage. Okay, so what if we put a little bit of charge on the positive capacitor plate? All right, how much energy would we get? How much more potential energy would you get? Well, if the voltage is V and we put an infinitesimal amount of charge, then we get an infinitesimal amount of potential energy. Okay? All right. Then we're going to use this equation right here. So this is the, let me just point out, this is a definition of electric potential. That's the definition of electric potential. We talked about that before. Then I'm going to take the fundamental, so this is the fundamental capacitor equation, Q equals CV. And we can divide both sides by C and get V equals Q over C. So now I have du equals dq times Q over C. All right, and remember, C is a constant. It just depends on the shape of this capacitor that we've manufactured. So then what we would do is we just simply integrate both sides. Okay, because we got a little amount of energy and we add up all of those little tiny energy amounts to get the total amount of energy that is stored in the capacitor. And so this is just like the integral of x dx, which is x squared over 2. So this is q squared over 2 is going to be that integral. And we get that the energy stored in the capacitor is q squared over 2 from this integral. And then we also have the 1 over c. So we get q squared over 2c. You can then, if you wanted to, you could write it as, you could take q and then replace it with cv. And if you did that, you would get 1/2 cv squared. Or you could take c and write it as q over v and plug it in there, and you would get 1/2 qv. So there's different manifestations. These all give the same answer. They're just, different ways of writing the same thing. So that is the energy stored in the capacitor. All right. So what I've talked about here is just kind of the physics of capacitors. Okay, this is the physics of capacitors. But when we talk about electric circuits, we kind of in an electric circuit, a capacitor is just represented as a thing. Okay, so we kind of like hide away all of the physics of what's actually going on inside the capacitor, and we just say it's a thing that obeys this equation and has a capacitance that is some number. Okay, so it's just a number. So the circuit symbol for a capacitor is really easy to remember. It's just this. I just got a text message. Just let me check it really fast. So this picture, it's really obvious. It's just here are the two capacitor plates and then the wires coming off of them. Okay. Even though in reality, remember, it's a three-dimensional thing. So you kind of have, like if I were to draw a capacitor three-dimensionally, it's like here's one of the plates, here's the other plate. Wow, that was horrible. This plate is kind of in the shadow of the top plate. So it's an actual three-dimensional thing. So when we are writing a capacitor in a circuit, we usually put its capacitance next to it. Okay. The value for capacitances are very small. It's a small number, okay? And the reason why is because epsilon naught is 10 to the minus 12. So you're taking area divided by a distance, and you're multiplying it by 10 to the negative 12. So you get a really small number. And so, C is, in most everyday circuit applications, you go to Fry's Electronics or something and buy capacitors. You can go there and buy capacitors. So they're kind of in the range. You can buy picofarad capacitors. So that is 10 to the minus 12 farads. You can buy nanofarad capacitors, which are 10 to the minus 9 farads. You can buy microfarad capacitors, which are 10 to the minus 6 farads. So, these are the typical sizes, all right? And these ones are going to be pretty big comparatively. These ones are super small and compact, but these ones are a little bit bigger. So, anyways, when we have capacitors, we can combine them in circuits. So we could have series capacitors. All right, so we could have a capacitor. We could have a capacitor C1, and we could have a capacitor C2. And just like with resistors, from the perspective of the battery, this looks just like a single equivalent capacitor, which I will call C sub S. All right? But here's the thing. Capacitors obey the opposite law from resistors. Okay? So you might remember that series resistors, you just add the two numbers. But series capacitors obey the same rule as parallel resistors. So 1 over C sub S, okay, is 1 over C1 plus 1 over C2. So it's the opposite of what resistors obey. And then if you have capacitors in parallel, C1 and C2 in parallel, that is equivalent to a single capacitor, which I will call C sub P. And the value of C sub P is, again, the opposite for resistors. If you have parallel capacitors, you add the two capacitances. All right. Yeah. So a common problem that I've seen on the AP Physics C exam is you have something like two batteries, or not two batteries, two capacitors are maybe hooked up in series to a battery, okay? So this is C1, this is C2, all right? And then here's the battery. Okay, now here's the thing about series capacitors. If we think about any charge that is on this capacitor plate, so maybe this is plus 2Q or something, had to have come from the capacitor plate above it that it's connected to. So then this one has to have minus 2Q, all right? And then this is plus and this is minus. So what that means is that series capacitors have the same charge on one of the plates. You know, the positive plate of C1 has the same charge as the positive plate of C2. Okay? So that means, so Q1 equals Q2. And so according to Q equals CV, that means that C1 V1 equals C2 V2. Okay? Furthermore, according to Kirchhoff's voltage law, if I go around this loop, the change in voltage has to be 0. Okay? And again, I have the positive and negative terminals labeled already because I just did that. And so if I go around this loop, I hit the negative terminal and then the positive terminal and then the positive terminal. So that means that negative V plus V1 plus V2 has to equal 0. Okay? So you can solve, so notice how we have two variables here. It's V1 and V2. And we have two equations. So you solve the system and you can get V1 and V2. So that's kind of nice. We could, yeah, so that's a common problem that I've seen. We could do the same thing with capacitors in parallel. So if you had something like this, and then you have C1 and C2. Now, one of the things I told you guys was that things that are in parallel have the same voltage. So that means that V1 equals V2. All right. And so V1 equals V2. And then using Q equals CV, we have V equals Q over C. All right. So this tells us that Q1 over C1 equals Q2 over C2. All right. So that's a nice equation. And then the total amount of charge is going to be the charge on this plate plus the charge on that plate. So we can take this and solve the system for Q1 and Q2. All right, so you can, you know, I've seen problems on the AP exam where you have to find the charge on the capacitor plate or find the voltage across the capacitor, something like that. I will tell you about one more problem before I end this lesson. And these are problems where you have a capacitor and it's either hooked up to something like a battery, okay, or it is not connected to anything, okay. Now, if the capacitor is not connected to anything, then the charge on the capacitor plate is constant. Why? Because the charge can't jump the gap. It can't go around. So whatever charge you have on the capacitor plate is constant. All right? It can't change from the value that it has. Here, because the capacitor is connected to a battery and the battery maintains a certain voltage, in this type of a situation, you have the voltage is constant. All right? So what these types of questions ask you is they'll ask, well, what happens to the energy in the capacitor as you do something? Okay? So in the case of Q equals constant, I am going to use this version of the equation because this has Q in it. And in the case that V equals constant, I'm going to use this equation. All right? So for this scenario, I'm going to use U equals 1/2 CV squared. And then for this version, I'm going to use U equals Q squared over 2C. All right? Now, in each example, I'm going to say, so what if you move the plates further apart? What would happen to the energy stored in the capacitor if you move the plates further apart? All right. So the voltage is constant. So the only thing that can change is C. Or the charge is constant, so the only thing that can change is C. So we have to look at what is changing C, or what is moving the plates further apart do to affect the capacitance, okay? And I can see right here, if we move the plates further apart, that means increasing the value of D. That means that the capacitance goes down, okay? Because it's on the denominator. So if the capacitance goes down in this equation, well, this has C in the numerator, so that means that so this implies that the energy stored in the capacitor goes down. Here, it's just the opposite. If the capacitance goes down, I can see that the energy capacitance goes down. Capacitance is on the denominator, so that means that the energy stored in the capacitor goes up. All right, so see how the scenario matters. What is constant within the capacitor matters. Another common thing is, what if you insert a dielectric? So you put a dielectric in. So putting a dielectric in increases the permittivity, okay? Increases the permittivity. So, and we can see that permittivity is on the numerator. So if we increase the permittivity, we increase the capacitance. So if we insert a dielectric, the capacitance goes up, which has just the opposite effect. So that makes the energy go up in this case, and it makes the energy go down in this case. All right. So what we'll be doing in the next lesson, and I want to say, Fu, if you're still there, thank you for watching. It's nice to know that you're around and still watching physics. I like that. So what we'll do in the next lesson is I will talk about circuits that have both resistors and capacitors in them. So those are called RC circuits. And once we start learning about RC circuits, we kind of can start to really start to do cooler things with circuits than to just have resistors. Okay, so that is my lesson, and